In section 2.3, we're going to look at a category of functions that are referred to as piecewise functions, or some books call them split functions, because that's actually what they do. They split. They're simply functions that change their behavior or their rule depending on where you are in the domain. So to help you understand that, let's first of all draw a couple functions in which the domain is all real numbers. So let's say we want to draw the graph of the function f of x equals x squared. Now that's a basic quadratic function, and if we were going to graph it, we'd have to first of all know what our domain is. So let's say our domain are all real numbers. In other words, all numbers from negative infinity to infinity. So what would this graph look like? Well, if we drew the graph of x squared, we know it's a parabola, and if we plug 0 in for x, we know it's going to go through the origin. We're going to get 0, 0. And as you increase or decrease the value of x, the answer gets squared or increases in size. So if we went over 1, we'd be up 1. Over negative 1, we'd be up 1. And of course, the same thing is going to happen if we go over to 2. We're going to be up 4, and negative 2 will be up 4. And so basically, we're just going to get a concave up parabola. And the graph is going to continue forever because the domain is all real numbers. So we could go over to x equals 3, 4, 5, 6, 7, and so far in the negative direction. And so this parabola is just going to continue to widen to the left and to the right as it moves upward. Now that's something that you would have graphed many times in your high school classes. And so let's take another function that's also very familiar to you. Let's take the function f of x equals 2x. And again, let's look at that for all real numbers. So from negative infinity to infinity. So this is going to be a straight line. And again, if we plug 0 in for x, we know it's going to go through the origin. And the number in front of the x, of course, is the slope. I'm referring to a form of the linear function that you're probably familiar with, y equals mx plus b. So the number 2 is going to be our slope, and the b, of course, being the y-intercept, which we know is 0. So this is just going to be a straight line that's going to rise 2 for every run of 1. So we're going to have a straight line that's going to look something like that. And the arrows on the line indicate that the line goes on forever, and the reason why the line goes on forever is because our domain is all real numbers. We can plug in any value of x we want and get a resulting value of y, or the function value. Now what we're going to do in this section right here is we're going to look at what's called a split function or a piecewise function. So what if the question had said, instead of graphing each of those individual functions over the domain of real numbers, what if the question had asked us to graph the function f of x equals, and then we open up a brace, and now what if the function behaved differently depending where you are in the domain? What if the function behaved as if it was the function x squared, but only for values of x from negative infinity up to the number 2 and including the number 2? And what if the function behaved as if it was the linear function 2x, starting at just past 2 and all the way up to infinity? You'll notice that the square bracket and the round bracket here, a function can't have, we couldn't plug the number 2 into both because then it wouldn't be a function. So what would this graph look like? And this is the purpose of section 2.3, is how would you draw that graph? Well, what you want to do is, the way I like to draw these is I like to take the point where the two functions are going to, where one picks up and one leaves off, the number 2. We're going to graph this function all the way up to 2, and then we're going to pick this one up just past 2. So the advice I'd give you for graphing these is start with this number right here, the number 2. If I plug the number 2 into the function x squared, I'll get 4. So if I went over 2, I would get 4. It should be right there. And it would be a closed circle because this function does exist at the point 2. And now what I want to do is going from 2 all the way back to negative infinity. So starting at this point right here, 2, and moving all the way to negative infinity, I want to draw the graph x squared. Well, that's why I drew this up here for you. Here's the graph x squared. This is the point 2, 4. So what I'm doing is I'm picking up my graph right at this point right here, and I'm graphing it from that point to the left. So my graph would just come down through the origin and turn around and head back up like that. So you see what we're doing is we're still drawing the graph x squared, but we're not drawing it over the domain of all real numbers. We're only drawing it all the way up to the number 2 and stopping at including the number 2. Now what we do is we pick up the other graph at 2x just past 2. So if I drew that one first of all separately, so if I just drew that graph, I want to draw the line 2x, but again, instead of drawing the entire line 2x, pick it up at the number 2, except it's not going to be right at 2. It's going to be, 2.00001. But for all intents and purposes, plug the number 2 in here, and you'll see that we get 4. So if I go over 2, up 4, I'm going to put this point right here, but this, it's not actually equal to 2. It's right up to, but not equal to it. So I'm going to put an open circle at the point 2, 4. And then starting at that point and moving all the way to infinity, I'm going to draw this line right here. Well, the point 2, 4, would be this point up here somewhere. And so I'm just going to pick up the graph here and draw it all the way to the right. So the graph would just look like that. But this is really just one function. Even though it's split or a piecewise function, you don't draw it as two separate graphs. So what you do is you put the whole thing together. Now imagine after you've done this a few times, or maybe even the first time, you probably won't draw them separately. But your final picture, the actual graph that you would draw, you would go over to that point 2, 4, you'd put a solid dot, and then you would draw a parabola coming up like this. And then when you got to that point, this graph would take over, and because they meet there, that solid dot would just be filled in, that open dot would be filled in by that solid dot, and then the graph would just take off like a line. And so you have a graph that basically is just behaving as if it was two different functions depending where you are in the domain. Okay, so let's have another look at another example of a piecewise function. In this case, it's the function f of x equals, and then from negative infinity up to and including 0, our function is negative x plus 2. And then starting at 0, just past 0, all the way to infinity, our function is the function the square root of x. So the strategy that I would adopt for this if I were you is I would just draw myself a coordinate plane. And then I always pick the number where the two functions are changing their behavior. So the number 0 here is the crucial number. This graph is existing all the way up to 0, and then this one is taking over just past 0. So I always start by taking that number and plugging it into my function. If it's a square bracket, that means it's including that number, and I would put a solid dot. So if I put the number 0 into this function, I get 2. So at 0, I have a solid dot at 2. And if I took the number 0 and plugged it into this function, I would get 0, but it would be an open circle. So that's where my two functions are coming together, at the value x equals 0. Now the rest of it is just your ability to draw graphs, and depending on how comfortable you are with that, this is where sometimes the questions can get challenging. But if you have a basic understanding of the shapes of functions, it's really quite simple. Now what I want to do is if I look at the first graph is linear. Negative x plus 2 is my familiar mx plus b. So the slope is negative 1. A line with a slope of negative 1 is falling as you move left to right, and the y-intercept is 2. So if I was to draw that graph, it would be a line coming down like this with a slope of negative 1, but I would stop at 0. If it wasn't for the fact that it was a split function, that line would just keep going forever. Then starting at the number 0, I'm going to pick up this graph, which is a root graph, a square root graph, and I'm going to graph it all the way to the right. Now if you're not familiar with this graph, you can always just plug in a couple numbers. Like if I plug in 1, I would get 1. If I plug in 4, I'd get 2. Plug in 9, I get 3. So what's happening is, it's actually a sideways parabola. It looks like that. And that is how you graph a piecewise function. They're really quite simple, especially if you have a pretty good understanding of the basic shapes of graphs. So let's finish off with one more. And I want to show you with our last example that you can have piecewise functions that actually are split into more than two regions. And so for our last one, we'll look at this one right here. The function is equal to -1 from negative infinity all the way up to -3, open bracket, and then 2x plus 4, starting at -3 and including -3 up to 1, and then negative bracket x minus 1 squared, square bracket 1 to infinity. So this is still a piecewise function. It's just that this time it's been split into 3 regions. But we're going to graph it exactly the same way we did the previous one. So just draw yourself a coordinate plane. And it doesn't matter which one you want to do first. I just like working left to right. So starting with negative infinity all the way up to -3. So here's -3. So starting at -3 and going all the way to the left, I want to draw the graph -1. Well, the -1 is a constant function. No matter what you plug in for x, you're always getting -1. So if I plugged in -3 into here, I'd get -1. If I plugged in -4, I'd get -1. So there's going to be an open circle at -3, -1, and there's going to be a horizontal line traveling to the left all the way to -infinity. Then right at x equals -3, this graph takes over because of the closed bracket. So if I plug -3 into here, I get -6 plus 4, which is -2. So at -3, -2, I'm going to have a solid dot. And now what I want to do is I want to draw this graph all the way to 1. So it's not a bad idea at this point to take the number 1 and find out where that would be. So if I take the number 1 and plug it into here, I get 2 plus 4, which is 6. So 1, 2, 3, 4, 5, 6. And that would be over at x equals 1. And that would be an open circle because of the round bracket. And then to connect those 2 points, you just have to draw whatever your function is. In this case, it's a linear function. So I'm just going to draw a graph coming up like this, hitting that point right there. And then right at x equals 1, this graph takes over. So plug the number 1 into here, and you get 0 squared, which is 0. So that graph is going to be right here at 1, 0, and it's going to be a closed dot. And then from here all the way to infinity, you want to draw x minus 1 squared. Well, x minus 1 squared is a parabola. You should recognize that from the squared. And the negative indicates it's concave down. Now, if you want to be more precise than that, you could plug in 2, 3, 4 and just get a few points. But basically, it's just a concave down parabola heading off like that. And so there you have it. That's the study of piecewise functions. They're going to become very important in our study of calculus. In Chapter 3, we're going to look at the study of limits. And to really understand limits, these piecewise functions become very important. So hopefully you'll have a chance to practice a few of these, and hopefully these examples have helped you to understand how that's done.